Record. So today I will start with the first lecture on sheaf theory, localization, and gluing. And this gluing is sometimes called by a name which is quite famous among non-experts as something hard and as something trivial for those who know it. It's what's called descent theory. Descent theory. So if you tell somebody who heard some 2 or 3 lectures on descent theory, especially people in algebra, they will say, "Oh, this is so technical," and so on. But anybody who really uses it considers it's very, very simple. So this is a technique of gluing categories, and which has been invented by Grothendieck, and which widely extends usual gluing of bundles, sheaves, and spaces, and which is usually expressed in terms of either Grothendieck topologies or more generally with some monads, co-monads, and some categorical tools. So we will have this more toward the end, but I will often express things about it. So actually everything what we do today is in some sense related to the descent theory. So that means gluing in a very generalized sense. So I do not know exactly what is the background of the audience, because the audience is diverse. So I will not go into very much details in the beginning of sheaf theory, because I know many of you know quite much, but I will go quite quickly, but I will give basic definitions. So I will start with sheaf theory. But I should also today, because it's the first lecture, have to explain also the third character of beginnings quickly. Beginning part. What's happening? Beginning quickly, but then more advanced more advanced features will be added, maybe with a little more care in the course. Sheaf theory, and then the third character is localization. Localization. So localization is a topic. If anybody I don't know, probably most of you are toward differential geometry, but if some of you are in algebraic geometry, then you know that in algebraic geometry you introduce so-called Zariski topology. And in Zariski topology, you are inverting certain elements in a ring and constructing open sets of a so-called spectrum of a ring. And this procedure is actually a beginning of something which is far more wide, and which is about that we have some space in geometry. So we have a space, and over that space you have something. What is something? Something can be, in physics, they like to talk about observables. Observables are things which can be measured over the space. You can measure, I don't know, positions of the particles and their paths, speed, I don't know, observables. Then in basic function theory, you have, of course, functions. Functions live over the space. But then you have more complicated objects. You can have, say, vector bundles. And today's characters, you can have sheaves. And you can have very sophisticated versions of these sheaves. I don't know, quasi-coherent sheaves. You have some analogs, so-called perverse sheaves, which are not even sheaves, and so on. So you have various things, and these things will usually group into some kind of objects. So observables and functions, they will usually form some sort of algebras. Now, first spaces of functions, but they also, usually you can multiply functions in every point. So they make algebras. And observables, if there's operators also multiply. And these things downstairs, vector bundles, sheaves, and so on, they organize into categories. That means, say, sheaves are objects, and then there are morphisms of sheaves. Vector bundles are objects, and there are maps of morphisms of vector bundles, and they will form categories. And now imagine that you want to consider same kind of objects. You are in the same world, but not over the whole space, but just over a part of that space. So I take, say, this part of that space. Okay. So I have these guys just over that thing. So usually in such situations, say if it's a function, so function is usually everywhere defined, or maybe is a sections of vector bundles or something like that. Then usually you can restrict here. So in this set, you can restrict. If you are working with spaces of algebras, you can restrict. And restriction for algebras or spaces, or spaces of functions, there is a restriction. But if you work with categories, then you will have some sort of functors which are analogs of restriction. So it's not that here every function will restrict here, but these kind of functors, you will have usually functors in both directions in geometry. We will learn toward the end of this course that we will have usually adjoint pairs of functors, and usually these ones usually embed here in the sense that you can simply usually extend these objects here in some sort of trivial way toward everything. There is more than one way, there is more than one, sometimes there are even two functors in this direction. And in this direction, you have some sort of, say you have a vector bundle, and then this vector bundle restricts to this open set. So that means if vector bundle is some v over some x, then if this is projection, then you take p⁻⁻1 of u, where u is a subset, and then you will have v restriction to u is simply p⁻⁻1 u, and then it has induced, you can also call it p or p restricted to p⁻⁻1 of u is the induced map. So usually these kind of functors in most of situations are the examples of these localization functors, and that's why they are called localization functors, because usually if you have some object like if you have say category of such objects like say sheaves, then from these categories you will get the category here, and that's you see the sheaves are the main kind of example, but there are very, very many other parallels between localization and sheaves. Actually, the construction of sheaves will also be some sort of related to some sort of a localization. But in algebra language, people also talk about localization. This is one simple one which people who were doing algebraic geometry know, that they take some ring of functions and then take some element there and then invert it. What does it mean, invert it? You see, if you invert some element in a ring, that means that you before you didn't have the inverse of this function in the ring, you have, or this element in the ring. Function is element of the ring of functions. That means you joined, before you had f, you had f square, you could multiply f by the other elements, but you could not find the f2 minus 1. But if say if this is a function, why function 1 over f wouldn't be in the ring of functions? Well, it isn't sometimes for a simple reason, because sometimes you have to divide by 0. So if you take the zeros of functions, say zeros of functions are here. This set here is the space, is the set, the locus where these functions are 0. So 1 over f cannot be in the space of functions because 1 over f doesn't exist. Simply, it's not defined here. But if you would restrict to this set outside, and this is exactly the way how the Zariski open sets look like, they are sets which are away from a locus of some some function. So you take this regular function which is here 0, and then outside of that, in this open set, in the complement of this locus, will be invertible. So when you add this r over f2 minus 1, if you add inverses of all functions which are 0 on some subset, some closed subsets, then you will exactly get functions which are now on this open set. So on this open sets, you have restrictions of all functions before, plus you have some new functions which if you would like to extend them to the whole space, you cannot extend them to the whole space because they have some singular locus. This 1 over f has a singular locus where f is 0. At that place, 1 over f becomes infinity. So indeed, singularities are the reason why you cannot extend. So you see, this is the essence of localization, which I told you in a very intuitive terms. I will of course give definitions and so on. So these are the characters of the course, which will be a number of lectures. Some are scheduled, some may be added, some may be recorded separately, so that I just put you some materials that you can have. But today we will have a little longer lecture. So let me go further. Let me start with elementary sheaf theory. For some of that, this part will be at the beginning boring, but I will go quite quickly. Elementary sheaf theory. By elementary, I mean on spaces, on topological spaces. I mean on topological spaces, because sheaf theory is also on Grothendieck topologies over Grothendieck topologies. So this is a little more technical for those who do not know. But there are also other generalizations. There are also other generalizations. For example, there is Sasha Rosenberg's Q categories, which are also kind of localizations in some sense. Oh, today this guy often breaks down. Rosenberg Q categories, etc. So first we look at topological spaces. So let's X tau be a topological space. I will do quite quickly for those who know. I think they will learn something new anyway. X tau is topological space. Then you define category of tau this is the category whose objects are open sets, and morphisms are inclusions. So you have a topological space, and you have subspace and another subspace U and V. And whenever you have U and V like this, you have this embedding, this inclusion of open sets. And this is morphism. And of course, they compose. So we say that a pre-sheaf on any category, C is a category, is a functor from C opposite. That means contravariant functor if you want, but we always work with covariant functors in modern category theory, from C op to usually to sets, to the category of sets. But we can consider also pre-sheaves with values, also with values in some other category, say D. So you have from C opposite to D. But then many things, some things work, some things don't. If it's just sets with additional structures, say groups or rings, then usually things work the same way. But for more complicated categories, some of the basic constructions which I will explain today will not work. For example, sheafification doesn't need to exist for pre-sheaves over a Grothendieck topology with values in some not so well behaved categories. So this is one object which will be needed much often, but I will not start with sheaves as pre-sheaves. I will start with a more geometric situation, which is nowadays called, and then I will immediately get pre-sheaves from them, which is nowadays called the Étale spaces. But before, if you take the classical book on sheaf theory, was Godman. Godman's book on algebraic topology and sheaf theory. It's a French book. It has a Russian translation very early. And I'm not sure if ever appeared the English translation. I'm not sure about that. So this is, I think, 1956 or so, book in 50s. Beautiful book for very basics of algebraic topology, the very basic steps, and very basic sheaf theory. And in that book, sheaf is what we today call Étale spaces. And I still, in my heart, sheaf is really Étale space. And pre-sheaves with some properties which are nowadays called usually sheaves is at least in the setup of topological spaces, in the sense of Grothendieck topologies, you have to work with pre-sheaves from the very beginning. So what are Étale spaces? First you introduce the notion of local homeomorphism. Local homeomorphism. So if you have pi from E to X, E can be now B for Étale, but in fact maybe at that time it was E was for espace, for space. So total space is E, and the base is X. Is a local homomorphism. Is a local homomorphism. Maybe I should have ready the draw line tool so that I can easily do things like that. Is a local homomorphism if for every X, maybe it's not good X, maybe it's better E because it's in space is in E. For every E in E, there exists an open set U open around E. U open is in E, such that P restricted to U from U to pi of U, and P of U is a subset of X, is a homomorphism. Okay, so let me go to the next page. So this is somewhat alike to covering space, but it's weaker. Remember, if you have a covering space, then you have a condition thing. You have a condition which is kind of different, which is similar but different. So here, what happens if I have a point E in E? You have a point. You have a pi of E, and for the covering space, it's different. For every point in the base, so covering space, you have a surjection from E to X. And if you have any point in X, so not only, so every point is, because surjection is of this form, but call it just X. So for every X in X, so this is surjection. And for every X in X, there exists V open around X, such that P to minus 1 of V is this joint union of open sets U alpha, such that U alpha is, so if you take pi of U alpha to V is a homomorphism for every alpha. So this looks very, very similar, but it's not the same as above. This is stronger. You see, you have in the Sheaves theory, you have open set here, and its image is homomorphic. In here, you have open set downstairs, and you take its pre-image, and pre-image consists of things which are homomorphic. Of course, in every of these points, you have still the same thing. See, you also have this little twirl, like here, but all these guys don't need to be equally big. See, it's not around this point, there is also some twirl which is homomorphic to its image, but maybe this image is smaller. Maybe you cannot choose one and the same. Here you choose one and the same downstairs, and in pre-image, all these are open sets. Okay, and and as far as this surjection goes, this is a little in modern when people were working tile space, this kind of tile spaces at the beginning, they also required that it's not only so a tile space is a local homomorphism, and originally it was required to be onto, but this is not here essential anymore. Nowadays, people skip this. So a tile space is basically a local homomorphism. So it is a space, this E, viewed together with the local homomorphism to some space X. And now there is a first observation that the images of sections, so this is, maybe this can be exercise, first exercise for those who never done it, exercise, sections, or the way I said a little bit ago, images of sections, images of sections. I didn't say what the sections. Images of sections are the basis of topology. It's called base or basis. Are the base of topology of EPX local homomorphism. Homomorphism, that means this is a tau. So images of sections are the base of topology. So what it means, all these twirls you see, etc., they will be the base of topology. So every open set is image is so what are sections? So if I have of local sections, so local section means section above some open set. So you have some u in X, and you have pi to minus 1 of u in E. And section is a continuous map. S is continuous. And S, if you first do S and then pi, you get identity on U. Or if you want, this is pi on pi to minus 1 of this pi. Okay. So this is section. So you take set of all S of X where X is in U. This is S of U. And this is this image of a section, image of a local section. Local section. Now, now you take you define f of u equals the set of all sections above u, sections S from E of u of the étale space, S from U to E. Yes, section. And you get a space of sections. Well, it's a set of sections, but let's put set of sections for now. Set of sections. A set of sections, and then you have a restriction. You see, we are the same topic which we had with localization. We are now having restrictions. So if you have U in V, inclusion, this inclusion maybe should be called IUV or IVU. Let it be I, and then we IUV. I think IUV would be better. Then if you take F of V, restriction on a bigger set, then every this section can be restricted to V. So you take simply U to V, and then you take section to E. You can consider section to like it's to E. I mean, I wrote it here just it has image in pi to minus 1, but it's you can consider that it has that it's in having values in the whole étale space. So I have from F of V to F of U. If this is I U V, then you get here some R U V. Sometimes they call it usually R as a restriction, but you can also sometimes call it by I star UV because it is some sort of induced by this I star. And this would be contravariantly, if UE goes to V, then F of V goes to F of U. So that's why it's upper star. And now if you see, if I have if I have 3 of them, and then the restrictions will compose, and you will get exactly that if I have R from V to W and R from U to V. And this is why the order is what am I doing? Of U to V in this one, I done wrong. R from V to U. So the composition is R WU. And here you see why we chosen IUV and not IVU. Because you see, if you look at if you write down this, then you see these ones are neighboring ones. It's like with matrices, the neighboring indices contract. So you just are left at the end with ones on the sides. So this is intuitive that you don't get messed up when you're dealing with this. So these are morphisms. So see, these are functions. If these are sets, if these are groups, this will be homomorphisms of groups. And well, I will require also compatibility with group operations at the level of étale space. If you want to have the group case, there is no problem. I can do it there, but we will now say that you get that this F and this F is associated to my étale space. To every étale space, you associate this F, which is a functor. This is a contravariant functor, which is exactly the functor from what I had before, from open sets overs of topology tau opposite to the category of sets. So F to every open set gives F of U, and to every inclusion from U to V, what we call it, UV or VU, VU, it was VU. It was IVU. Is mapped to this RVU from F of V to F of U. Now this, the point is that we can go other way around. But also a more sophisticated point will be that in one direction we do not lose information, in another direction we can lose information. So if I start with a tau space, then I can always get to other way around. Then I get this pre-sheaf. So this is a pre-sheaf, but this pre-sheaf is nowadays called pre-sheaf is nowadays called sheaf, and before a tau space was called sheaf because it has a special property, and I will explain this property. But other way around, you can start with any with any pre-sheaf. So P from UV tau opposite to set is a pre-sheaf. So just contravariant functor. Pre-sheaf. Contravariant functor. I mean, it's covariant functor this way written. It's covariant from opposite category. That's contravariant functor is covariant from opposite category. And then you can form the tau space by saying by defining the étale space, namely you have to define this E before we had this E over X. So I have to define what are the points of this. Points of this will be germs of sections. What that means? That means that that you look at the pairs. Look at the pairs. U, where U is open in X, and the point. So U is open in X, and X is a point of view. And sorry, I'm not done. And you have S, UXS, you can say. So an S is is element of P of U. And you would like that this is you would like to put this as an element in this space, like a local section is almost like a point if it's small enough, you know. So that means that if you have a different one which agrees on it around you would say around this point, so around X. So if I restrict to some smaller open set, so if I have another V open around the same X and some T, then this is equivalent if by definition if there exists W open in U open intersection V open in such a way that that S restricted to W around X, that's important because it has to really be centered about this point, as a W is equal T a W. This is the relation of equivalence. And then you will because if U and V and some V prime agree, then this agree on some neighborhood and this they agree on some neighborhood, then the first and third will agree on the intersection and so on. And then these classes will be points of E. These classes will be points of E. And how to define the projection now? New page after. So E consists. So these guys are called germs. So these are germs. In fact, we are here passing to a direct limit construction from the point of view of category theory, and E consists of germs of local sections, this equivalence classes, local sections. Better to say, if you look at all local sections around X, so if you take all X S around X, and you take all classes of those, all equivalence classes, then the space of all such will be called, well, it's maybe not because this was E, which come from P, we can call maybe this PX. And in general, if you have a tau space E over X, then the pre-image of any point X in X will be called a stock over X or stock above X, or stock at X, stock of the tau space, or more often they say stock of the sheaf. So stock of the sheaf is basically maybe it wasn't completely clear, because this restriction, I was writing like functions restriction this way. By this, I should have said that this S restriction to W, this is in terms of because we started with P, and P P was a contravariant functor, and so if S was from, say, U to well, before was from U to E, but now S is simply abstract element of P of U, and this should be element of P of W, and the restriction, so W to U includes, and then here we have this from P of U to P of W, you have R from how it was from U to W or to W to U. You see, you always, if you start with U, then U is always on the right, if U is the smaller open set. So W to U. So this is simply UW of S. Or if you consider this functor, that that you would also call it P for function, that would be this R of UW. That's also, if you would call everything by P. So here I have functor which U sends to P of U on the objects, but every U to V sends to this from P of V to P of U, this RVU. But maybe if you would just call it P, this functor, then it would be P of this inclusion EVU. So you might start with such a language that you have only P in the notation, and this restriction is kind of in use in sheaf theory. But if you are just working with abstract functor, abstract contravariant functor, then sometimes you have just letter P. But then when we think about, we think like if these are like functions, these sections are really sections of something, and they will be sections of something because they can be represented by a tau space as well. So S on W is RU W of S, and this is pi of I W U, or UW, sorry, UW. Okay, so so let's continue with that. So this way we get E. So what will be the projection? Projection is trivial. So this EP is set of this equivalence classes, or it is union of this PX, of this stocks overall X. So simply all PX goes to X. So if E belongs to PX, then E simply goes to X. So the whole stock, all those which have this component X, simply forget U and forget S, forget the section, and you go back to X. And then on E, now before that was an exercise. I didn't do it, but I expect that if you have never seen it, do it. It's very, very useful. Whenever you have a tau space just from this property that is local homomorphism, it's easy to get that the sections make a base of topology. That means every open set open sets are exactly the unions of images of the sections. So here I put that as a definition. I simply on E define a topology where U in E, maybe it's not good. I mean, today I'm not reserving U to the base or to above. For me, U, V, whatever I say. If I say here U is in E, U is subset of E open. I will not have a special kind of letters for the open sets in total spaces. For once in the base space, some people like to have a different kind of letters upstairs and downstairs. So if you open so where U in E, or maybe better to say U in E is open, maybe define a topology. U in E is open by definition. If U is an image of a section, so what that means? You know, so if U is if there exists if there exists section from P of we already know what is this projection. Projection is already defined. So take pi of U, that's open set in the base. If there exists, so pi of U has to be open. If pi of U is open, and there exists S in P of pi of U, such that X is in U if and only if X equals S of pi of X. Okay, so this is exactly the image of section of its projection. So you just forget. So this U are some classes of the form U pi, and it's always the same S. Or sorry, U, and here is some say Y. Maybe it's better that I called here E. I mean, it doesn't matter that it's good how it's written, but maybe this is more suggestive, because here I was say Y is like pi of E or pi of X before was. You take Y is in the base in U, and you take all such ones for all Y's. For all Y's in U, you take classes. You take this class, and you take the set of all this, where Y is in U open. U open. This is alternative description. It's clearly the same. This is the way you construct them. You take a section downstairs, you take all points, and for every points you take it germ of that section at that point. doesn't need to be here. Here the whole U, but I could put a smaller set and restrict S to this, doesn't matter, but it's the same class. But I could also, this here is, the first definition is the way you define it from above, that you simply take a point there, I mean, you take some set above that, you project, and then you say, oh, I can return back by a section exactly on that open set, and downstairs it has to be an open set. Or I can say, topology is made of all sections. For each section, I know the U, I know the open set. So this open set can be called simply S. So for you take so S of this is the that means of course that means U pi of E S. Here I'm already free thinking in terms of étal space as a set. The section is now defined. Before my section was an abstract element of pi of U, but now this section is simply, if I have this U, then by section I get into E in such a way that simply to every point X in U, I take the germ of S at X, so UXS. So take its germ there, and that's the function. So this description is exactly the same as here. I mean, this here is just a notation. It's a notation, and this notation becomes exactly this composition of functions once you talk in terms of étal space as a set. So people talk about these things interchangeably, whether either in this language or in this language, we talk interchangeably. But if you start with pre-Sheaves, then you really have to talk about germs as classes, and if you and then when you define these classes, then you define the section simply this way, and then you work with set theoretical sections, and you have a topology. And then it appears. So it's again exercise. We obtain local homomorphism. Well, this is quite simple. You see the equivalences are only at every point. So if you have two germs at different points, two germs whose projection is different points. So this is a germ of a section at point Y, and if you have some Y prime, you have different points. So certainly it's easy to see that this thing, and this is by definition open set, is in bijection with the open set U. And this bijection in one direction is a section, which is simply this, and in another direction is a projection, which simply forgets U and S, because U and S are fixed, you see. So it's a bijection. It's very easy to see that it's bijection. Now, now you have to look at the topology of this. Downstairs, you have an upstairs. So upstairs, basically, you have to downstairs. It's kind of obvious. You take open subsets, and you have again sections, and you have restrictions, and so on. Section and restrictions, and You can very easily see that that it's actually homomorphism. But you have to play a little bit. It takes 10-15 minutes to write it down. It's just the right exercise. Other way around, you see. So well, but so what we had from pre-Sheaves, you get into étale spaces, and this will be a functor. Because among pre-Sheaves you also have morphisms. If pre-Sheaves is a functor, morphisms of functors are natural transformations. And for étale spaces and continuous maps, pre-Sheaves and natural transformations. And here étale spaces and continuous maps. And then this here, you can take inclusion of categories. You can take this is a subcategory of all simply maps of so let X be fixed. The base be fixed, but these étale spaces over the same base, and these pre-Sheaves are, so in fact X and tau is fixed because we want to have also topology downstairs, but topology upstairs will be anything. So you have all this E over X, and these are simply maps of topological spaces over X. And if you take E and E prime, then such a commuting triangles will be morphisms, and these are morphisms. So this is continuous map from E to E prime, such that here's P of E, here's a P of E prime, and they commute. So you have this category. This is a slice category of topological spaces over X. So all topological spaces over X. And now I have a function other way around. So say topological over X. I will have a functor into pre-Sheaves and natural transformations. That's this functor here, which I will. What is this functor? This functor is it's not difficult to describe it. And here will also inclusion. First. So if you have E over X, not necessarily local homomorphism, just a continuous map. X tau, it has a topology which is fixed for the whole diagram. Then you simply, to this, you define space of all local sections for every U in the category of open sets and inclusions. You define all sections over U. So all sections from U to E section, local section. In this theory, we'll just say section, although it's a local section. And so we said above that this is a pre-Sheaf, but we also said that we have because we had these restrictions and so on. So we also have U to V maps to R from RUV. restrictions. So we have also this and then if you take two different E2, E prime or X star, then you have to look. So here some F from E to E prime. Then you have to look what happens with the, can I do something about this pre-sheaves? So I have this pre-sheaves. So this is one functor from U tau. So this is pre-sheaf. Well, it's not good to call it P, because P was like a generic one, and this has to be related to E. So maybe I can simply call it. Well, we can maybe we can call it PE, and then we have PE prime. P prime. So you have, what are sections here. What are sections here. These U's are in the same topology downstairs. And so this came from a section. This is S from U to E. And here are sections from U to E prime. So it's clear that from this one you can get here. So by post-composing with E prime, okay. So you simply go in this direction by sending S to F composed S. Now, so you have a functor, because if you have two of them, you have composition, then, so this is a covariant. So this is a covariant functor. And then this composition, it's essential image. So if you take just the objects which are in the image of this map, we call these, so these are pre-sheaves with sheaf condition. Pre-sheaves with sheaf condition. Sheaf condition. And these are exactly, so as you see, you have two categories. You have pre-sheaves and spaces top over X. And you have functors here, and you have some intermediate thing. And then we see that these two functors are in fact adjoint functors. And these adjoint functors, if you restrict to this middle parts, then it's equivalence of categories. So objects in any of these equivalent categories are called sheaves nowadays. So we have two languages, tau spaces and pre-sheaves with sheaf condition. Modern people just learn the second one usually, and the first one here a little bit. And topologists, old school, like more tau spaces. But in fact, you have to think in both terms. Algebraic geometers also like in more classical kinds of algebraic geometry, they like more tau spaces. But this here is more flexible for generalizations. So let us state this a little more about this junction. New page after. So we have this this X star, and we had pre-sheaves pre-Sheaves, pre-Faso. So pre-Sheaves, and then you have, so we had two functors. One was from pre-Sheaves to spaces over X. Another is, and here I have this category which is nowadays just called Sheaves, and here étale spaces over X. And here we have equivalence of categories. The above two functors restrict to equivalence of categories here. This is the whole point of elementary sheaf theory, is this diagram. But what is this? What is this? This pre-Sheaves with sheaf condition. Well, if you have a section which is in P of U, and you write U as a union of some smaller open sets, U alpha. So U is open, U alpha is also open in a topology. Then S restricted to U equals T. Well, let's have two of them, because usually they say when it's 0, but that's for sheaves of groups. But here I don't know what is 0. So we have S and T. S on U is the same on as T of U, if and only if, well, doesn't need to set a restriction by this point because they are defined on T. We can say just S and T. But here I need to say S on U alpha, I'm sorry, is T restricted to U alpha for every alpha. So that means, because you see, why this is true for guys which come from étale spaces, because you see when they are the same as section, you see these sections came from true sections in that case, and true sections, you know, they have to be the same at all points. And to be the same, that means if you if it's the same at the point, and then it's the same around that point in some open set. That's easy to see in for étale spaces, that if you would have two different sections which are the same at the point as germs, if their germs are the same, that means that there exists some W there where they are the same. Because here I look at germs. This is pre-sheaf of, okay. So so that's first. And second condition, so this is some sort of a uniqueness, and we call it, if only this is true, we call it separated pre-sheaf. Separated pre-sheaf or mono pre-sheaf. This mono pre-sheaf is usually in generalizations, use terminology in some generalizations. So this is some sort of uniqueness, but then there is also existence condition, or some epi-pre-sheaf condition. This is a rarely used term, epi-pre-sheaf, but it's useful. Epi-pre-sheaf, So if you, again, U open is union of U alpha open, and given family S alpha. So not, here we have S and T globally defined in the whole U, and then I look at their restrictions and compare them here. And here it's a different situation. I take S alpha, which is in P of U alpha. These are a priori different things. Alpha in this index set A. Alpha in A. Union alpha in A, I can say. And given this, such that you take S alpha, and you see you take U alpha beta, which is U alpha intersection U beta. I will say about generalization very soon. And then you look at P of U alpha beta. And of course, you have R from you restrict from alpha to alpha beta. To P of U alpha. What am I saying? I wrote it wrongly. I wrote you restrict from a bigger open set to smaller open set. From U alpha beta to U alpha. So such that, and if you look at here, no, it was correct. It was correct. U alpha is bigger. Before I was thinking in terms of indices, and then I started who is bigger, and then alpha beta looked bigger than alpha. No, U alpha beta is intersection. You see, this is U alpha beta, and then so if S alpha is here, I can restrict it here to S alpha restricted to U alpha beta. This is nothing else than this R, this restriction of S alpha. So S alpha restricted on U alpha beta, this is simpler to write, but in terms of this function, or you can say P of I or whatever, we have another notation, is S beta on U alpha beta. Okay? So, and given such, there exists S, it is unique by one in P of U, such that S restricted to U alpha is S alpha for every alpha. Here was for every alpha and beta. Now, you see, you could put this as one condition, these two conditions as one condition. I could simply see there exists unique. Because if you call this as alpha, then you have to glue in a unique way. Another way around, from there exists unique section, so they glue and they glue uniquely. So this is an example of gluing which is in descent theory, but in the descent theory is a little more general for many reasons. First, they are not open sets, but they are more general situations. Grothendieck topologies, comonads, and so on. There are other tools for gluing, but there is also this phenomenon. You see, I have this U alpha, I have U beta, and then you have this U alpha intersection U beta in both. But in fact, you see, say you can consider this U alpha, U beta, these inclusions into U as being more fundamental than U alpha and U beta. it's good to think in terms of morphisms. And then when you think in terms of morphisms, then you say why this needs to be inclusion. It may be a more general, maybe more general map. Maybe there is more general class of maps. But then in any case, if you look at families of such things, then you remember when I had P of U to P of U alpha, we have a restriction. So this map is in opposite direction. So we call it R, but we also could call it, and once we wrote this, as I star from U to U alpha. Like it's a contravariant thing. So now I have this U, I have this U alpha beta. Now you can imagine that this U alpha beta can be constructed from these two inclusions. If I know how they sit in U, I know how to intersect them. And this would be basically that you would take U alpha to U, here you would take U beta, you take I beta, I alpha. Now, if I write P of U beta, P of U alpha, you have this I star alpha, you have here I star beta. And then we will have here this, this will be U alpha cross U beta over U. It will be basically, these are all, it's like a Cartesian product where we identify, what am I saying? Well, we have to do it a little carefully. So we look at the points in the intersection. We can look at these are points in U alpha and U beta, which will go to the same point in U. So you take a point X alpha, and you take some X beta, and it becomes the same in U. In U, this abstract sets you can compare only when they sit in U. Then that's X in the intersection. So that means, so these are all pairs of U in U alpha cross U beta, but such that they become the same in U. And this makes sense for more general maps. And then if you look in such a way, then it's not, then you can have this U alpha cross U beta to U beta and to U alpha. You see, this can be more general, kind of more general situations, more general maps. And then in such situations, you really have to be careful in which way you go in which way you consider these elements in this double intersection. And then even this situation, so this situation is a little more general, but then there is, in descent theory, there is even more general situation, say non-commutative geometry. Non-commutative geometry is what we had at the very beginning, in a way, this way of thinking that instead of space, you are thinking of all these guys which live above, all observables, functions, vector bundle sheaves, and they define the space. If you take this philosophy that you define a space by saying what objects live over the space, that's called non-commutative geometry. So this can be even things which are not, over space you have functions, they always commute. But if you take some non-commutative algebra, you're not sure that these are functions over space. But you are thinking of a space as being represented by these objects above. And in these situations, you can, instead of this product, which I had here at the end. I had this product. You can have kind of two products. So I can have, instead of having a set P, you see set of functions P of U. This was just a set. There are situations where you can consider a category, or you can consider module. You will see this in localization theory later. So we have some, say, M on U, you have M on V, and then you can kind of see how this looks like on the whole space, and then localize to V, and you will get certain MUV or MUV, but you can have also MVU. These are like two different intersections. They are not really intersections. They are not fiber products like this one. They are different. These ones are different. And you have maps like here and like here. So you have two kind of intersections. So not this intersection, not this a little bit more general, but even you have two different ones. Think of this open sets as interleaving. Once U is above V, this is below. Another, this is above and this is below. And then you require, when you are gluing things, gluing means you want to get the global object. You see this global section is glued from the pieces as alpha. If they agree on common intersections, they define a global S that exists as such that S on U alpha is S alpha. If you have a family of S alpha which agree on U alpha beta. So when you would reconstruct like this construction above basically says that if you have such a diagram for all U and V, and you have maps like that, and then you take inverse limit, which say just limit in modern category theory of that, and you have this is M. And if this is true for U's and V's, in a more general situation, then we will say that M is glued from these pieces. That means, and this is an example of generalized descent, that you really can, all objects, these are now objects in a category. Here I have a set and set of elements, and here I will have a category of all such M's. If all M's in certain category of modules or sheaves or more general objects, glues in the sense that I can obtain global objects from local objects which agree on the kind of intersections, if I can glue them together by the limit construction to a single object M on the union of all these UVs. So if this is U alphas, UVs, all possible pairs, for this is diagram for all possible pairs, but they belong to certain family and I can define a family, I get the global one. So there is a gluing condition. So can you define objects, the category of all objects globally if you know them locally? So this passage between local and global is the whole point of this descent theory and of these special objects like sheaves, and then there are some categorifications like stacks, and in fact this here is some statement in the which is, well, if you have a category of such things, and if it glues everywhere where you need it, then it is some sort of a stack-like condition. So let me return to this. We have 10 more minutes today, according to the plan that we finish in 12:15. But as I said, we have today only one lecture because of my misunderstanding when the lecture starts. So we skipped the coherent state second lecture today, and we make this lecture longer on the sheaves. So let me return to this adjunction. So I have this adjunction. So what does it mean, injunction? That means that, so we have to have some names for these things here. And so if I go from, I really don't know how to call it in this particular situation, but if I go to from pre-sheaves to topological spaces and return back, so you go from pre-sheaves to topological space over X, and you always end in étal spaces. Remember, if the essential image is here, this is essential image of this functor above. And this here is essential image of this functor below. So that means that you have functors here and functor here. And then I have a composition from pre-sheaves to étal spaces, topological spaces over X, but these are in fact étal spaces. And then I return back to sheaves. And this functor here is called the sheafification. Sheafification. Also, if I go from topological spaces over X to pre-sheaves, I mean, I end in sheaves already. This is, and then I get to here. I get to étal spaces over X. This also improves the situation. I end up in étal spaces. Now, if I have a junction, if you have two functors, say you have some function f and functors f and g from C to D, then what is a junction can be said in two ways. So let me see which one. So if I go from, say, from pre-sheaves to sheaves, every sheaf is a pre-sheaf, so here you have inclusion. So this here is also a pair of adjoint functors. And this one is maybe the best to remember first, that this that here's this A, sheafification, I will call it A. It's very often called A. I don't know why A. Sheafification. Then pair of adjoint functors means that one is left, first one will be left adjoint, another is right adjoint. And this one will be the right adjoint. Say no, sorry, this is a left adjoint. This is a left adjoint, and this will be the right adjoint. So F is left adjoint. We say F is left adjoint to G. It can be said in two ways. One way is to say that there are natural transformations between FG and identity and GF and identity. Now, so if this is, if F is left adjoint, then we talk about, so let's see, identity is here on which category? I go for first G, then F, so identity is on D, and here is the identity on C. So I have from identity of C to GF, and from FG to identity of D. I have a natural transformations. So this one is usually called the unit, and this is called a co-unit. And in this situation, where the right one here includes into the left one, the epsilon is iso. That means that every component of this natural transformation is an isomorphism. And if in a pair, the left one would be included in the right one, in that case, the unit would be an isomorphism. So this here we say a reflective subcategory. So Sheaf is a reflective subcategory. And this A is an example of localization functor. So this Sheafification is a localization functor. It has a different meaning in the sense, well, it's not completely obvious to see. There is a way to see it, but it's not completely obvious to see that it's analogous to the situation when I had the restriction, say, of something to a subspace. This is different. But there is a way to view it in a very parallel way. There is a generalization of, or in a way, there is a generalization of construction of a standard construction of a localization in module theory and Sheafification, where Sheafification and localization are described in a unique way, in the same way. The only thing in localization, you use some sort of, we say, additive Grothendieck topologies. They're called the Gabriel topologies. In this case, you are using usual Grothendieck topologies. And topological spaces, they are topologies in the sense a special case of Grothendieck, induces a special case of Grothendieck topologies. So, and this epsilon and eta satisfy some identities. We like to actually call not F and G, we like to call F upper star, F lower star. Like these are part of the same morphism F. And this pair of functors together is like one morphism, because if two functors are adjoint one to another, then if you tell one, then another is determined up to isomorphism of functions, up to invertible natural transformations. So it's enough to say one of them. The another one is then determined. So if you have F upper star is left adjoint to F lower star, then you can go from lower star to lower star, upper star, lower star, and back to lower star. Here you go by eta. You see in this first, you from F star is the same as identity component with composition with F star, and do F star. That means if you take F star of some M, you go to you do eta on F lower star M. That we just concatenate functor, the notation for the functor and natural transformation. We mean this. If for every object M, we go to this goes to F upper star, F lower star, upper star, F lower star M. And then here we have F lower star, and this in second part we contract epsilon. That means to F star M, it means you do F star of epsilon of M. So this is a morphism. To this morphism you apply a function and you get a morphism from here to here. And then this composition has to be the same as identity. And one more like that. If you start with F upper star, you can go to F upper star, F lower star, F upper star. But now in the second part, you see here, I insert unity. So this is F upper star eta. That means F upper star M. You are sending by F upper star of eta M. This is component of natural transformation eta at m, and I will say next time what this. I mean, you can figure out what these are in the case of étale spaces, etc. This epsilon and eta are easy to construct. Just work in terms of sections, and you will get them immediately. F upper star m, and then you contract in the first in epsilon f star. That means epsilon component at f upper star m goes to f upper star f lower star of that sorry to f star m. This goes from f upper star f lower star of f upper star m to f upper star m, of course. And this thing also has to be identity. It's a triangle transformation. Well, people usually like to talk in different way. They say for any two objects, I forgot what is C, what is D. So I think I had from C to D f upper star and f lower star from D to C. So for every, so there is a natural transformation, there is a bijection natural in both variables between homes. And here I take f upper star of anything of C to D, where C is object in C and D is object in D, to C f lower star D. So this is left, it's on the left side, here's left, here's right. And this here happens in the left if the D is right. I mean, f cetera is on the right side of this too, but this is a category in category C, and this is in category D. And you have a bijection of this set and this set, and this bijection is natural in C and D. Natural in C and natural in D. So there is not only that there is a bijection, but you have to check that it's for every morphism here. I mean, you have to see that it's natural in this object C and object D. And this is equivalent to saying that this here is identity of upper star. That these two triangles work. So it is more practical to construct this epsilon and eta, because with them you can really calculate. With putting here bijection is useful, and it's when people were doing very simple constructions, they were having very simple junctions, then they like to talk in this language. But nowadays, when people have more elaborate calculations in category theory, I mean, it's much more convenient to work in terms that f upper star, f lower star, that this junction is given really in terms of epsilon and eta. So that means that you have these two functors, and you have two natural transformations which between f upper star, f lower star, and identity and f lower star, f upper star, which satisfy this triangle identities. And this once you really construct from so you make this composition, how much this differs from just doing nothing. And then you will see that there is a map in one direction. So say you have a points of original, say if you are at this space, in this space, and you look at the point in the total space. Then you consider a section through that point, whose such that this point is in the image. But then you look various sections through that point, and you look at their germ. So what's the relation between? So you can do what's the relation between this germ and the original point. So we want to define certain maps using such, and similarly here you start with a point in pre-sheaf over U that will be some section, and then you look at its germ, and then from these germs you are making again section, and you again compare, is there some natural map defined by comparing this. So by these ways, using sections and germs, you will define epsilon and eta. So the whole point of elementary sheaf theory is that you have this diagram that you have between pre-sheaves and topological spaces over X. You have a pair of adjoint functors, which restricts to an adjoint equivalence of categories between sheaves and étale spaces, where sheaves are pre-sheaves with the two-sheaf condition, the separatedness and the epi-pre-sheaf condition, and étale spaces are those topological spaces over X which are local homomorphisms. And that's the point. That's all elementary sheaf theory is just to elaborate on this. And then what is interesting, of course, now are the categories of such objects. If you have different topological spaces, if you look at various kinds of inclusions, open inclusions, closed inclusions, depending what kind of setup, algebraic geometry. So you look, and maybe sheaves or sheaves with structures, sheaves of modules, quasi-coherent sheaves of modules, and so on. And then there are various functors among them for various situations when you have a map of maps or inclusions and so on. And these are usually also given by some adjoint, by some functors which have adjoints, and sometimes they are parts of adjoint triples and so on. So a lot of geometry can be explained by using these junctions among the categories of sheaves, these further ones, and by abstracting those to more general situations. So this is very central in modern geometry when we look at spaces which are equipped with various either structure sheaves or complexes of sheaves or categories of sheaves and so on as very important geometric data. So this is what I wanted for the first lecture on sheaves localization and gluing. I can now stop recording. Maybe somebody will have questions. Where do I stop recording?